Thank you very much, Heidi. Yeah, thank you very much for having me at this seminar devoted to optimization. However, as you may think, okay, process mining, data analysis may not have that much in common with optimization. We do have some sort of optimizations in our field, maybe not a classical setting of optimization problem, but still some things that I want and would be happy to share with you. So let's start. First of all, I have to acknowledge that this is a joint work together with here at the University of Adelaide, together with Professor Lewis Mitchell, Professor Matthew Rohan. So we were working on this problem together. But yes, so my initial area of research is process mining, and that is what I'm going to talk first of all. Then I will talk about performance analysis and how this can be related to optimization problems in process mining. And then I will introduce some new techniques we are working on. So these techniques are related to the analysis of the performance of processes. In other words, the execution times. And then I will summarize my talk. So first thing is process mining. So this is an area or sub-area of data analysis that deals with event logs. So we may have different kinds of information systems. This can be banking system, websites, government systems, and they all record their behavior as they execute some cases, and they produce some sort of event log. So here you can see a simplified version of an event log. So we have some case IDs. This can be, for example, some sessions on our website when user uses the website. So the number of the session can be a case ID, or any number of transaction in the banking system can be case ID. Then we have activities. These are atomic steps. What was happening? So we logged in, we clicked a button, whatever. So these are activities. They have labels, ABC, so they have names, and we have timestamps. And the goal of process mining is to take this input data, event log. This can be huge event log, and then to produce some kind of model. Different languages are used. So here, for example, we can see a simple flow chart diagram. Here is a BPM annotation that says first A is executed, then we have two parallel branches. In one, we have a choice between B, C, and D. In the other, we have F or nothing, or we can skip it. Then we have synchronization, and this is the last event. So this is a very simplified version. And usually when we introduce process mining in such a way, the common question is, why do you need this? Okay, we discovered a model. So why do we need this model? Why not to deal with the event log? Why we need to consider this? So first of all, this is some kind of generalized behavior, and there are two, at least I see two goals. First, nice visualization. Now we can see what is happening in what order. And another thing that is commonly that is used as a common motivation for process mining is that, okay, we can actually look how the process works and we can optimize it. So we can find bottlenecks, we can find some tasks that take a lot of time, and if we will put some effort to perform them faster, we will optimize the overall time for our process, the overall execution time. So this is another thing, and this is what I'm going to talk about now. So not only we are interested in these nice colorful models, we also want to know how to make our processes run faster and how to make them more optimal. And of course, there are lots of tools in process mining. So for example, here you can see two screenshots of the so-called tool DISCA. DISCA is available for academics. So for University of Melbourne, University of Adelaide, you can download DISCA tool. And you can upload event logs there, and you can get this nice colorful diagram. So here, for example, on the left, it shows some frequencies. So what are the frequencies of these transitions between the events? So we first do this, then this. What are the frequencies here? Another shows time. So actually it says years. So don't be scared. Years means like overall. So when we sum up all the cases together. So maybe I can show how it works. If I stop sharing, can I, and switch to Discord? Let me show. So here is the Discord tool. I hope you can see it now. So here's some sort, you can see. So here's some sort of performance analysis. So and actually what this process is, so this is a real world event log. And this is a university event log. So when employers try to get refund for the conferences and so on, so they somehow should provide an evidence that they visited a conference, then these documents should be approved. So this is a several step process. This is how we get our refunds for traveling. And here we can see some information. So median duration of this transition, mean duration of this transition, maximum and so on, and total. And this is a sort of performance analysis we usually see when we deal with commercial tools for process mining. So let me go back to my presentation.
There's one question, Anna.
Yes, sure. Thank you.
What was the years for as a total? Because it seems the median is seconds, but the total is years.
Right. So this is a generalized behavior. So that means years. So for example, we have how many 11,000 cases there. So if we will sum up all the durations, 11,000 durations, we will get 26 years. I don't know if it's useful information or not, but this is how it works.
It looks like a frequency of this event or this process.
Yeah. So we can get some information from the event log on the performance of the process. But of course, the question here is how to improve the process. So this is how the event log actually looks like. This is the perfect representation or visualization of the event log. How to improve the model? What are the bottlenecks? What if we will change this time? This time. What will be the overall time? We know the overall time for the event log, but how to play with these values? What if we will put some effort into improving times for one of these steps? How will the overall time change? And this type of analysis is called what-if analysis. So this is a kind of, as I said, a motivation for process mining. We build these models from event data to find problems and to optimize our processes. But still, this is a just representation of an event log, and we want some kind of analytical solution here. Some model that will give us an answer. And of course, so this is another screenshot of a very popular tool, which is called Salonis. So here again, we have these durations between the steps. We have different kinds of analytics and so on. Again, representation, mostly the representation of the event log. This can be very helpful, but we want to run a what-if analysis. And of course, researchers did a lot of work regarding this. And here is screenshot. Here you can see a screenshot for one of the research from 2015. So this is a stochastic Petri net. So this is a net discovered from the log and annotated with probability density functions of time durations. So this is something more detailed that we saw before in the commercial tools. So plenty of works here, but actually these works were mostly focused on the simulation. We discover a model, we discover these times. So because for different cases, the time duration for each step can be different. So this is how we get the probability density function. So there should be some distribution. So we get these distributions, and now we may try to change this model to see if we get better results. But for this, in this particular example, we have to run simulation. So this is not an analytical solution. We change these times, we simulate the model, and we get some kind of distribution. But this relies on the simulation. And I'm particularly interested in an analytical solution. So suppose we have discovered such a stochastic model. What is the solution? What will be the overall time from start to end? So this time should also have a distribution. What will this distribution will look like? So I'm considering the following setting for my problem. So have an event log, and the first thing we can discover is a Markov chain where we have states. States can be our activities. We move from one to another with some probabilities. So this is a simple Markov chain. And we can annotate this chain with time distributions for transitions. Not mean time or median time as we saw before, but as in the previous research with some time distributions. And such models are known as semi-Markov process models. So why is that? Why semi-Markov? Because in Markov process models, all distributions are exponential. Semi-Markov allows more flexibility. It's a more general model. It says that it's semi-Markov because it only follows one of the Markovian's rules. So we move from one state to another. We are not dependent or without any dependence on the past. However, here for the transitions, we do not have exponential time distributions, and this is where one of the Markovian properties breaks, and that is why these models, more general models, are called semi-Markov models. So we can discover these models, and then we can run different types of analysis, and the ultimate goal will be to build such overall probability density function, so the overall distribution for the time of our process. And since if we have such a model, we can change it, and we can each time we run our analysis and get some insights. What will happen if we will improve the process in this or another way? So I'm going to consider and to propose two types of analysis. So the first one is called express analysis, which quickly analyzes the Semi-Markov model based on the mean times of the transitions and gives us the mean time of the overall process execution. And another is a full analysis. It's a different type of analysis that takes a Semi-Markov model discovered from event log and then builds this probability density function. So let's start with the express analysis. Express analysis, so consider again an event log and consider the first order Markov chain. So in first order Markov chain, we depend only on the current event. So we do not depend on the past events. So we move from one state to another. Each state corresponds to one event only. And we get these probabilities from frequencies of the transitions between the events. So first thing we do here, we filter our event log according to cases. So here, for example, we have case one. That means that we have claim, then we have assign, then we have resolve. So this is kind of some kind of a process. Then we have close, and we have this sequence of events here. And we also annotate the transitions with frequencies, which after normalization will be probabilities. again, we then add case 2 here, case 3, and so on. And we also add two states, which will be start state and end state. So what we are interested in now is the time from S to E. Now I'm going to present a technique that will help to get the mean time from S to E, knowing the mean times in each of the states. So first, to calculate this, we need to build a so-called irreducible Markov chain. So what is that? This is just a totally connected graph. So each state should be reachable from any other state. And for this, what we do, we connect the end state with S, and we set the probability to 1. So when we finish with our case, we start all over again. So this is how the model will look like. And this is called irreducible Markov chain. So totally connected graph. And so actually, this approach to build an irreducible models, automata models from irreducible automata models from arbitrary automata models was proposed by Artem Polaviani, with whom I was working at the University of Melbourne. So he also did this. However, we didn't have probabilities. So here is a model with probability. So it's a kind of not an automata model, but a Markov chain. And we applied the same trick here. We can also build a so-called second order Markov chain when each state is a pair of the previous events. So we now say what we are in state 2, for example, if we saw events claim, assign. So now each state depends on the length or the history that we consider is 2. And this is also what we can do here. So usually, as we increase the order of the Markov chain, the model becomes larger because now there are more possibilities. And indeed, in some cases, it really makes a difference whether this the history makes difference, because this can be different states with different mean times, because we depend on the history on what was before. So this is a simple approach of how we construct Markov chains from event logs, and there is nothing new in this in process mining. And here you can see an example of a Markov chain of order 1 constructed from a real life event data. So this is a process of Volvo IT where they analyze some problems during the production. So when a problem or issue is raised, then it should be handled by one of the employees. And this is how this process goes. So this is a real data, not so many activities here. And for this, we can calculate actually the mean execution time. So the results are presented at this point at archive. So how we can calculate this mean time? We can calculate the limiting probabilities of the states. So what is the limiting probabilities? So here they are denoted as pi's. So I is the number of state, pi I is the limiting probability of the state. It's actually the frequency of the state. In irreducible models, we can cycle in the model forever, but what if we will stop at some point in time? What is the probability that we are in state 1? What is the probability that we're in state 2? So these limiting probabilities can be calculated, and they actually reflect the frequency of the states in the model. And to calculate the overall time, so actually we discovered the following formula to calculate the overall time for the process when we start in S and we end in E. And we know the mean times, which are presented by mu here. We know the mean times for each of the states. And we know, and we can, depending on this probabilities, we can calculate limiting probabilities of the state. And basically, what does this formula say? It says that the mean time of our process, the mean time for moving from state S to state E via some other states can be calculated as a weighted sum of mean times for each of the states, but weights here will be the limiting probabilities. So how frequent is this state in our model? And this should be multiplied by the mean time. And once we have this formula, we can play with this formula. We can, for example, say, okay, what will happen if I will reduce the mean time of one of the states? How this will affect the overall mean time of the process? Or if I will change the probabilities here, I will change the limiting probabilities of my state. This is another way how we can improve the process. So this formula actually says that there are two ways how you can improve the process, optimize it. First, you can play with the mean times of the states. Second, you can change the structure of your process. Maybe it can be more optimal. And this is what pi stands here for. So this is how we can calculate and play with these models. And again, real life example. So here is a vector of our states. For each state, we have its limiting probability, pi, and we have mean time for each of these states. So how long we stay in each of the states. And applying this, we can easily calculate the mean execution time. So here, for example, for this event log of Volvo IT system, when they are trying to resolve some production problems from the start, then the case is accepted till the end, then they finally realize what has happened, what was wrong in the production, and solve this issue. So the mean execution time will be around 12 days. But now the question, so now we can play around. We can say, okay, what will happen if, for example, accepted will be performed 2 times faster? If someone will click the button accept, I claim this ticket, I take this ticket. What will be the mean execution time, and so on. So how we can change the process? Can we remove some redundancies that will lead to the change of these probabilities and to the change of limiting probabilities of the result? So this is a kind of express analysis that we can use to analyze the overall mean execution time for our process. Do you have any questions here? Maybe in chat?
Can I ask one?
Yeah, sure. Thank you.
So you, so for the mean, you divided by pi s. I think pi s is starting event.
Yes.
Because everything goes through that.
Yes.
You don't use the summation of all pi's because it's quite equivalent with that. Yeah.
Yeah, correct. Yes. So very nice observation. Thank you. So why do we need pi s here? Because we have to divide this time by overall how many times s was executed, and how many times s was executed is corresponds to the number of the cases. We just normalize by the number of the cases that we have here.
Because from E every time it goes to S. Okay. So
Yeah. But we need this irreducibility here. Otherwise, we can't calculate pi's, or we can, but the model will be so it will degrade to some states if it's not irreducible, and we need this full cycle. And moreover, we need to be able. So you may say, okay, but you just can go from S to E and calculate using some frequencies. But you see, we have internal loops here that we also have to take into account. And this general approach allows to do that.
Thanks.
Thank you for the question. Yeah, so that was an express analysis for the mean times. But what about in general? So in general, it would be interesting to see the overall density function, probability density function for the overall time, not only the mean. What is happening in general? And to do that, we consider semi-Markov models, as I said before. So they are represented by probabilities that we transition probabilities from state to state, and by probability density functions for times for each transition. So, for example, consider transition self-loop transition from state completed to state completed, where it is this one. We can go through our log and collect all the times in between completed and completed, and we get some kind of sample that we can build a histogram here. You can see, and you can see that actually this is not exponential distribution. It has two modes. It looks like we have to apply something non-Markovian here. We can't deal with just continuous Markov models where we have exponential distributions, because it turns out in real life event data we may have these different peaks, and we have to deal with that. And this is where we can apply semi-Markov models where we have no restrictions on the probability density functions. And we can take this histogram and we can fit the curves here. Another example, here is the transition between completed and queued. So this one. So again, we can try to fit. And actually the model that I've chosen is a Gaussian mixture model. So that, what is that? It's a really simple model because it says that the distribution is just a weighted sum of Gaussians. That's all. So here we have a weighted sum. So the sum of coefficients is 1, and each gy here is a Gaussian with different means and different variances. So this is how it may look for this transition. Oh, sorry. This is, oops, I'm moving the wrong direction. This is also the mixture of Gaussians. I have some Gaussians here, some Gaussians here, and this is how I can approximate the transitions, the times for transitions between my states. And here, actually, you may see that for some distributions, we get we may get negative time. So I played around with different models, and I understood that I can live with that. I will truncate the final solution, and still will get some result. Yes, a question?
Yeah, I think Peter has a question.
Yes.
Yeah, sorry, the question was about the negative times, which you then just went on to answer. Although it sounds like you still use the negative times in the computation, but only truncate at the end, or you truncate each individual one? Okay.
I thank you very much for the question. I truncated at the end, so I've tried different things. So I can, unfortunately or fortunately, I carry this negative through till the end, till the final execution time, and truncate at the end.
Okay.
And still get some results. Why I didn't? So there were different ideas. One of them, why not to truncate? So we can build a so-called truncated normal distribution here, but it doesn't have that nice properties of Gaussians that I use when I'll calculate the overall time.
Yeah.
But, yeah. So because Gaussians are really easy to deal with.
Sure. Yeah.
This is one thing. Yeah. Another idea that I was thinking that I have to here I have to squeeze it to take this first Gaussian, which allows negative times, and to squeeze it closer to 0, changing variance. But I didn't like the end result. So it turned out that just Gaussians that allow negatives gave me better results.
Okay, thanks.
Yeah, thank you for the question. Yeah, so we pick every transition, build these distributions and try to approximate this with Gaussians. And what's happening next? So this is just a fragment of a semi-Markov model. For each transition is annotated with a pair probability plus probability density function. And what we do next, we remove states one by one. So for example, here we want to remove state 2. So what would it mean? that would mean that we actually can get from 1 to 4. We did it before via 2. Now we remove 2 and we draw an age between 1 and 4, annotating it with new probabilities and new density functions that are calculated as convolutions, because now we had time from 1 to 2. We had time that was distributed according to this function. We had time from 2 to 4 that was distributed according to that function. Moreover, in general case, we may have self loop here. So overall, we now need to estimate the time from 1 to 2, and we do this via convolution operation. And this is one more reason why I applied multi-Gaussians, because for convolution for them is really simple. The mean is the sum of means, and so on. So there is no need to consider some kind of Laplace transforms and back, like what could be done. So I decided to just to test a simple case. What will happen if I will just use mixture of Gaussians, convolution calculated easily in one click, in one operation? So because now maybe not in one click, because they in real life they turn to be really long, because mixture of Gaussians are several Gaussians, and then you multiply them. If you had n and m, you will have at the end you will have n by m multi-Gaussians, because you consider all the possible probabilities there. Anyway, so computationally that turned out to be not so time consuming. And what is happening at the end when we reduce node by node, except S and E, two special states that we injected artificial states, we get a model that consists of two states, S and E, and they're connected by an arc with the final result. And we can see, and actually this final result is the overall time. So I've applied this technique to real life event data. And this is what I've got. I've tried different orders of semi-Markov models. And actually for real life data, we can see that Markov models, although being more general than event logs, because in event log, everything depends on the overall history of what was before. It's a finite number of traces. In Markov models allow everything that was in event log plus more new paths. Anyways, so these models able to find some peaks, especially closer to zero, probably because here we still have less number of steps that could be discovered by Markov models. Here is and here, by the way, the truncation at the end. So here is a semi-Markov model also built from another event log. So yeah, sorry, I didn't say that. This is histogram of the event log, and I put this probability density functions of semi-Markov models on top, and still the approach is able to find the main peaks in the event log. That means that in somehow, although being more general, these semi-Markov models can find this frequent times, and they are different, of course, for different order, different Markov model, different orders of Markov models give different curves. However, still, I can see some visually. We can see some peaks that correspond to peaks in the event log. Also, yeah. So here is the truncation at the end. So no zero values, and somehow to estimate is it good and bad. Okay, visually maybe we can see some similarities, but what's really happening here? So I calculated for real life data some Kyle divergences, so this is a measure that's that we can use here to find the differences between two distributions. What is the difference in observed and expected behavior? So observed, this is the event log. Expected is our model, is our Semi-Markov model, our approximations. So we calculate these values, and actually it's not that bad. So the values, the spectrum of values that I received for different order of Semi-Markov models, I find it quite okay. So the closer to the zero we are, the better. But still, if we, so this is actually what's happening here. This is the expected value of log of the relation of two probabilities. So these are expected values of the logarithmic function of the relations of these two probabilities. And actually that's the logarithm is natural. So overall, it says that P is quite close to Q here, which is okay. So I keep working on this, to go thoroughly through all the real life event logs I can reach, so that that are publicly available, and to provide more details. The open question for me here still the relation between the order and this divergence, because this is not changing the order of the Markov chain from 1 to 5 doesn't give me a better solution. So it jumps around these values back and forth. It's not like it's monotonically better if I increase the order of the Markov chain, or is it monotonically worse? It's a kind of still a kind of interval where I can get these divergences. So summarizing the work. So we developed two new methods for the analysis of the estimation time of the whole process, basing on the history, basing on the event log. So my real hope is that these methods can be used for the optimization and what-if analysis, because now we may say, okay, we want to change the time for this state, for that state, for this activity, that activity. What will be the result? And the result can be calculated, and we will see the difference, and we will see how we can improve and how we can optimize our process. So I'm testing these methods on real world event data. And as I said, for me, next steps will be, I will try to find the relation between the order of Semi-Markov models and the accuracy of the results that I get. And another important next step that I didn't mention here is actually there is another thing. There is a huge assumption for all this research is that the cases are not related. However, they may be related, because if our company has only several employees that handle the cases, if one employee is busy, that means that we will have a delay for other cases. So cases actually can be interrelated, and it would be interesting to consider queuing models when we have a queue of maybe orders, queue of requests, queue of cases, and how this will affect the time, and how this can help in the for the analysis of the overall process execution time. So I get it. I have a good performance, right? So I finished earlier. Oh no. Okay, thank you very much. Yeah, and thank you for having me.